So torque is super cool because it is the rotational version of force. So again, we're just comparing translation and rotation. So here we have the rotational version of force, which is torque. And it's super cool. And it's basically, well, the formula for it, this is very, very simple. It's just the radius vector cross the force vector. Super simple. So again, for people who maybe not heard of cross products and stuff like that, it's basically there are two vectors, right? Let me just set up a scenario for you. You have a pivot point.
Isn't it R cross F?
Yeah, that's what I said.
You said that force cross R.
I said
That's
radius cross. Did I not say radius cross force?
I thought you said it the other way around.
Well, I'm sorry. I meant radius vector cross force vector, right? Now, for all these scenarios, you need a pivot point. So we have some point, and a pivot point basically means that something is rotating around this point, right? Point of rotation, axis of rotation, whatever. So we have a pivot point, and we have some part where we're applying a force. The easiest scenario to think about, if you aren't able to imagine anything right now, is a door. A simple door, right? Can act exactly like this. So in this scenario, your hinge, where your hinges are, is your pivot point, and where your handle is where you're applying the force. So I think people can already imagine the scenario. You push it, and it creates some amount of force, and that is what we quantify as torque. And again, the cross product is, again, just a vector product, basically, because at the end of the day, torque is a vector quantity, right? And all it represents in this case is the amount of, again, you can think about it as rotational force is being applied to said system. And again, you can kind of see something interesting from here, the relationship between the torque and the force and the radius and all this good stuff. Keeping the torque constant, we have F and R basically inversely proportional in a way to think about it. And that is why on every door, you never see your handle at your hinge, right? You see it the farthest away from the hinge because you apply a small force at a great enough distance and you can do anything you want. I brought up a quote because this is a very famous one. Everyone, this is your Archimedes quote. Give me a lever long enough and a fulcrum on which to place it, and I shall move the world. I believe it was him that kind of did this whole. Was it? I'm pretty sure. I mean, how else would he have said it, right? Because he kind of discovered this whole thing where, hey, if I'm far enough, if my radius is long enough, I can just apply a tiny force, and it will relate to a ginormous force on the other side. If the other side radius is very tiny, right? Mm-hmm. Does that make sense? So yeah.
I wanted to say that because torque is a vector quantity, but the magnitude, I guess, quote unquote, the magnitude, because this can also be a negative value. Mm-hmm. Anyways, like the amount of torque that you're applying is force times the radius times sine of the angle between the two.
Yeah, that's the cross product formula, right?
Yeah, but just the number, not the vector.
Yeah.
So what this actually means, and if you think about it for 2 seconds, I feel like that I say that every single episode.
2 seconds. No one thinks about it in 2 seconds.
If you think about it for 2 seconds. So imagine your door, okay? The vector for the radius goes from the hinge to the handle. If you apply a force in the same direction of that radius vector, you're going to be applying zero torque because your door is not going to be rotating at all. And that's where the sine theta comes in. If your theta is 0, then mathematically you're applying zero torque. And that makes sense because if you're pushing, in the same direction as the door is not going to move. But if you increase the angle at which you're pushing on the door, you'll notice that you're going to get the most torque when you're pushing directly square onto the handle, when you have a 90-degree angle. And then, of course, it decreases until you get to the other side and you're pushing into the hinges, towards the hinges of the door, where you will also have zero torque. And if you know what a sine wave looks like, that's exactly what I just described. So that's how when I get into a problem that has to do with torque and all that, there are 3 things, or maybe 2 things, that I think about. First of all, you need to look at the pivot point, the point of contact, and also the angle of contact. Okay? So the pivot point in this situation would be the hinges. The point of contact is the handle, and then the angle is just how, like, at what angle you're putting your arm on the handle. And that's the only information you need to solve any problem. And you can take this idea with the door and apply it to anything that rotates. And that's all the information you ever need. Mm-hmm. There was this difficult problem, or I guess it was difficult at the time, in our physics lab, where we had to describe the motion of a yo-yo, where we put a yo-yo on a table and you rolled up the string, and then what we had to do was pull on the string at different angles and write down what the yo-yo did, and then we had to, like, explain it mathematically. And unexpected things happened, right? You'd pull on the string and the yo-yo would start rolling in the opposite direction. Mm-hmm. The tricky thing about this problem was that I wasn't using my own advice right now, and it's to think about the point of rotation, the point of contact. The point of contact in this situation, because the center of the yo-yo is not a single point, right? The center of the yo-yo is a cylinder, and the string contacts the outside of the cylinder, right, in the center of the yo-yo, which means that from the center of the yo-yo to the point of contact was the radius vector. And then depending on which angle we were holding the string at, right, we did like a horizontal one, we did a vertical one, and also like wrapped around on going the other way, which means that the point of contact was on the top instead of the bottom. We also did a couple of different angles. The point is the point is I was expecting it to be super easy, like, oh, I pull on the string, the yo-yo is just gonna follow, right? But it turns out it was very counterintuitive, and it made me think about these torque problems in a different way. And now I actually think about it for 2 seconds, and it helps me a lot. So, I encourage you to do that too.